All right. Today we are diving into something that could totally shake up the world of AI as we know it. It's a brand new architecture called CANs. And get this, it's an AI that can actually show its work. It promises to crack open that infamous black box and let us see exactly what's going on inside. So let's jump right in. Pretty much all the AI that runs our world today, from the LLMs you chat with to the tech in self-driving cars, it's all built on a piece of technology that's, believe it or not, over 60 years old. It's called the multi-layer perceptron, or MLP, and for all its power, it's got this one huge secret problem. And that problem? It's that these things are a total black box. For decades, we've kind of just shrugged and accepted that we don't really know how they get their answers. You put data in, you get an answer out, but what happens in between? It's a complete mystery. So this new research poses a really exciting question. What if we could finally build an AI that could actually explain its own thinking? Okay, so let's dig into that. To really get why CANs are such a game changer, we have to first understand this whole black box problem with the current champ of AI, the MLP. MLPs are basically the workhorses of deep learning. I mean, they are everywhere. You look inside those giant transformer models that power things like ChatGPT, and you'll find MLPs doing a ton of the heavy lifting. And look, they work. They're super effective. But that power comes with a pretty big price tag. So here's the deal with MLPs. First, they are just incredibly parameter hungry. That means they need millions, sometimes billions of tiny little connections to do their job. But the bigger problem, the one we've been talking about, is that they're almost impossible to understand. We know they work, but we can't see how they work. We can't follow their logic. And that's not just annoying. It's a massive roadblock for making AI safer, for fixing it when it breaks, and for using it to make new scientific discoveries. And this is exactly where CANs come in. The researchers behind them basically said, okay, let's throw out the old playbook and start from scratch with something totally new. And when I say fundamentally different, I really mean it. It all comes down to the math they're built on. See, MLPs are inspired by something called the Universal Approximation Theorem. The basic idea is, if you make a network big enough, it can learn pretty much anything. But KNs, they're based on a totally different idea, the Kolmogorov-Arnold Representation Theorem. This one says that you can take any really complicated function and break it down into a bunch of simpler, one-dimensional pieces. It's a completely different way of thinking about the problem. So what does that actually mean for how these things are built? How does that math change the design? Well, the core innovation is, honestly, both super simple and incredibly profound. This is where it gets really cool. In a normal MLP, all the smarts are in the dots, the nodes. Think of them as little calculators doing a fixed job. The lines connecting them, the edges, are just simple wires that carry a signal strength, a weight. KNs flip this completely on its head. The nodes are now super simple. They just add up what comes in. The real intelligence, the magic, is now on the edges, the connections themselves. They're not just simple wires anymore. So what exactly are these smart edges? Well, they're these flexible, learnable functions called splines. Here's a way to think about it. An edge in an MLP is like a rigid pipe. You can open the valve more or less, but that's it. An edge in a KAN is like a super flexible hose that can bend and twist into any shape imaginable to perfectly fit the data flowing through it. It's not just learning one number, it's learning the entire relationship between 2 points. That right there is the secret sauce. Okay, that all sounds really cool in theory, right? A totally new architecture. But the big question is, does it actually work? And more importantly, does it work better? Well, the paper gives us some pretty stunning results that suggest the answer is a huge yes. So the researchers threw CANs at a really tricky problem from pure mathematics, predicting a property of knots called their signature. A big MLP, one actually developed by DeepMind, managed to get about 78% accuracy, which is pretty good. But the CAN, it sailed past that, hitting almost 82% accuracy. Now, better is better, but that's not even the mind-blowing part of the story. You see, that MLP model from DeepMind, to get to that 78% accuracy, it needed around 300,000 parameters. We're talking about a big, complicated network here. And the CAN that got a better score, it did it with just 200 parameters. Let that sink in. Not 200,000, just 200. It wasn't just a little more accurate. It was more than 1,000 times more efficient. This is huge. It means CANs seem to get way smarter, way faster, with way fewer resources. And that incredible efficiency is what unlocks the real magic here. Because the can is so ridiculously small, and because its smart edges are just curves we can look at, we can literally open it up and see what it learned. And in this knot problem, the can basically pointed out that the answer depends almost entirely on just a few key variables. Bam! An instant, valuable insight for mathematicians. This is it, an AI that actually shows you its homework. This is way bigger than just solving one math problem. This ability to not just spit out an answer, but to actually reveal the hidden structure of the problem itself, well, that could completely change how we use AI for science. What's just wild is that these cans can actually learn the basic building blocks of math. By looking at the shapes of those squiggly lines on the edges, researchers can translate what the network learned back into an actual symbolic formula. You know, the kind of equation a physicist or mathematician would write on a chalkboard. And that's exactly how the researchers put it. They see cans not just as a tool to crunch numbers, but as a true collaborator in the process of discovery. I mean, think about it. An AI that can look at a pile of data and suggest the actual scientific law that governs it, that is an absolute game changer. Now, let's be clear, this is still super early stuff, but the potential here is just massive. And not just for scientists, but for the entire field of AI. The paper itself lays out a super exciting roadmap for what's next. Like, could we swap out the clunky, inefficient MLPs in today's language models and create something new, like transformers? Could these networks help us crack some of the toughest unsolved problems in physics? They even think cans might help solve one of AI's most annoying problems, called catastrophic forgetting. That's when a model learns a new trick and completely forgets everything it knew before. So what cans really represent is a whole new direction for AI. A future where we don't have to choose between models that are powerful and models that we can understand. We can have both. And if our most powerful AI tools can finally start showing their work, just imagine what we'll discover next. The next great revolution might just be a partnership between us and our machines. This is for entertainment purposes only.